This is part 2 of the series Transformations, and in the last part we looked at translations, and we're going to start this part out with the idea of composition of transformations. A composition is nothing more than a group of two or more transformations combined to form one single transformation. And before we move further, we need to solidify some of the concepts from the past. The first one is the idea of what a translation is. And that comes from the translation postulate. And it's a statement of the obvious, but it says a translation is a rigid motion. And we need to understand that because we're going to use that idea to move forward with some of these other transformations. Remember that we had stated that a rigid motion is a transformation that preserves angle and length. And so therefore, if we look at the composition of rigid motions, we know that a composition of rigid motions is also going to be a rigid motion, and that is the composition theorem. So a composition of two or more rigid motions results in a rigid motion. Using these ideas, let's go ahead and look at an example of a typical composition of transformations. In this example, we have triangle PQR, and this is how our composition is presented. It looks like a pair of transformations in the form of translations. Before we actually apply these transformations, I want to look at a dynamic example and show you some things that may not be intuitively obvious at this point about compositions of translations. So let's go ahead and take a look at a dynamic example and see what we can figure out. What I have here is two transformations, one translation here and another translation here. This first translation is 5, 3, 5 in the x, 3 in the y. The second one is 2 in the x, -1 in the y direction. So the intermediate, this one in here, was 5 over 1, 2, 3, 4, 5, and up 3. And then from that, we translated that over 2 more and down 1. Now what I'd like to do is I would like to show you what happens if we reverse the order of these transformations. That is, if we make the first one 2, -1, and the second one 5, 3. Where did the images end up? Well, first thing I want to do is put a marker over the top of this image so that we know where the first one ended up. So I'm going to create a marker here, and it's now over the top of our first actual image. This is the image after both translations have been done. Now let's reverse the order. We're going to make this one 2, -1, and this one 5, 3. So make the first one 2, -1, there, and the second one 5 and 3. And look what happens. They end up in exactly the same place. Now the reason is, if you take a look at the combination of these transformations, what's happening in aggregate is you're adding 2 to the x and then 5 more. So that's actually an x plus 7. And then you're subtracting 1 from the y and adding 3, which is a total of a +2 in the y direction. So these two transformations should be the equivalent of one transformation, 2 plus 5, 7, -1 plus 3, +2. So a 7, 2 transformation. So let's go ahead and do that and see what happens. So I'm going to make this the intermediate. I'm going to make that one a 0 transformation. And then we're going to go 7 and 2. And notice with a 7, 2 transformation, we're back over the same place. So that's why the order for translations doesn't matter in this particular case. Now, Don't make this generalization that the order of all transformations isn't going to matter, because it is. But in this case with translations, that's all you have to do is combine your X transformation with your Y transformation and you'll get an identical result. So let's go back to our first example and let's work it with this information in mind. We have point PQR in a triangle, and I want to write down the coordinates for P, Q, and R here first. So point P is 1, 2, Q is 3, 6, and R is 6, 4. Now let's go ahead and apply the first transformation. So P prime, we're adding 3 to the X, so that's 1 plus 3 is 4, and adding 1 to the Y. 2 plus 1 is 3. Q prime is 3 plus 3, which is 6. 6 plus 1, 7. And R prime, 6 plus 3, which is 9. And 4 plus 1, 5. Now let's apply the second transformation. So P double prime is 4 minus 2, which is 2. 3 plus 2, 5. Q double prime, 6 minus 2 is 4. 7 plus 2 is 9. And R double prime, 9 minus 2 is 7. And 5 plus 2, 7. Now we could have accomplished the same thing by aggregating these two here. Because they're both translations, the order doesn't matter. So we could have said 3 minus 2 is 1. So the overall transformation then would have been xy goes to x plus 1 and 1 plus 2, y plus 3. So if we want to look at what that would look like, starting from this point, we had 1, so our P prime, double prime, if we were doing this, would be 1 plus 1 is 2, 2 plus 3 is 5, same as this. Our Q double prime, 3 plus 1 is 4, 6 plus 3 is 9, which is the same as that. And our R double prime would have been 6 plus 1, which is 7, 4 plus 3, which is 7, the same as that. So when you're dealing with the composition of translations, you can make the choice whether you want to do them individually or in aggregate. All right, let's move on to reflections. Here we have a representation of a reflection, and the definition of a reflection is the movement of each point of a figure along a line perpendicular to a line called the line of reflection, a distance equal to the distance from the point to the line of reflection. Now that may seem a little cryptic. Let's take a look at it over here. This line is the line of reflection, and it's the line across which each point is being moved. Now if you take a look at point A, this distance that A has to move to get across this line of reflection is going to be equal to the distance it moves as it's reflected. So this distance and this distance are equal. So notice these two segments are congruent. And the line through point A, A prime, is perpendicular. Notice the perpendicularity sign here is perpendicular to the line of reflection. So you can think of this point as being translated along a line perpendicular to the line of reflection, and it's being translated by a distance equal to its original distance from the line of reflection. So A goes to here, and then it goes an equal distance down to here. B goes down here and an equal distance to B prime. C goes this distance here and then an equal distance to C prime. So that's the idea of reflection. It's mapping the points along a line perpendicular to the line of reflection. And this distance is always equal to the reflected distance. So let's take a look at a postulate that's related to this. And as you can see, when we reflect this figure, nothing in the figure has changed. Because we're moving along a line perpendicular and we're moving an equal distance, this is a rigid motion. The figure is not being changed in shape or size. So the reflection postulate says a reflection is a rigid motion. Now, if we were to combine what we've talked about in the past, a translation, with a reflection, we would have what's known as a glide reflection. And a glide reflection is a composition of transformations with a translation followed by a reflection. So the glide is the translation and reflection at the end. Let's go ahead and look at an example and put the idea of reflection to use. In this example, we have triangle PQR with these coordinates. Let's go ahead and graph that first. So P is at 3, 1. So here's 3, 1, 5, 1, and 5, 3. So there's our triangle. And we'll just make a really bad triangle here. I don't want to take the time to draw one formally. All right, now we're going to reflect that across the line y equals 0. Well, y equals 0 is just a horizontal line at y equals 0, which is simply the x-axis. So we're reflecting it across the x-axis. So what we have to do is determine the distance. So there's a perpendicular segment going from here down here, perpendicular to the line of reflection. The line of reflection is the x-axis. It's moving a distance of 1 unit. So 1 unit from there is down here. So since it's 1 unit above, it's going to be 1 unit below, 1 unit above, 1 unit below, 1, 2, 3 units above, 1, 2, 3 units below. And that is going to be our image. And if we want to write the points, we had P as 3, 1, Q as 5, 1, and R as 5, 3. Now what happened? When we reflected across the line y equals 0, or across the x-axis, what happened to the y coordinates? Well, let's write our our coordinates and see what happens. P prime is the same x coordinate, but the y is negative. But it's the same value. Q prime is 5, negative 1, and R prime is 5, negative 3. So the transformation notation for reflection in the x-axis is going to be, so a reflection in the x-axis is x, y goes to x, negative y. So we take the same x value that gets copied, we take the y value, and we change its sign. And that is a reflection in the x-axis. I'm going to end this part here, and in the next part, we're going to work a couple of more reflection examples just to make sure this idea is solidified. So I will talk to you in the next part.